Hello everyone, my name is Jin Lin, and I'm a PhD student from the University of Notre Dame. Today I'm going to introduce my paper, Supporting Program Comprehension through Fast Query Response in Large-Scale Systems. So during the development of software projects, engineers will create many artifacts along with the source code, such as requirement, test case, design definitions. Traceability is a technique to establish and recover the missing links among these artifacts. So with the support of traceabilities, the engineers can ask trace queries such as how is the feature implemented in the project and whether this function is covered in the unit test. With the help of the traceabilities, the engineers have a better understanding of the code and the project progress. However, conducting the traceability in practice is very challenging and arduous. It requires a lot of manual efforts. So to address these problems, the researchers have proposed automated trace models to alleviate the manual efforts required in the traceabilities. However, most studies had focused on improving the model accuracies, where none of the works in current communities focus on the scalability of the trace models. But actually in the enterprise projects, there's tons of artifacts which will create a very large search space for the trace models, which makes the traceability unpractical to use in real projects. So in this paper, we address two key aspects of the querying software projects from the scalability perspective. The first task is that we want to automatically generate the trace links among artifacts to provide the just-in-time spot for the user queries. And in this case, trace links between the artifacts are missing, and we use the trace models to generate the links for the missing part. And for the second task, we are issuing the project level queries over a large set of existing trace links. And these links already exist. We will leverage the links to generate the answers for the user queries. So as we have discussed, the project in the large industry project usually have a large number of trace links. We therefore propose a big data processing techniques to accelerate the computation for the trace link query execution and link generation. The workflow of the trace tags in our approach will be firstly converted into a direct acyclic graph, which representing the dependency among all the operations. And then we will optimize the graph into a pipeline with reduced duplication. This procedure is automated by our heuristic-based method. And then by obtaining the pipelines, we will feed this pipeline to the Spark machine learning framework and to conduct the computation with the Spark underlying functionalities to achieve the maximal parallelism. To make evaluation and comparisons, we compare the Spark-based method against the conventional Java library-based implementations for the trace link generation. And we compare the Spark-based query execution engine with the Java queries and queries in the SQL database and graph database to see which can achieve the best performance. So specifically, we select MySQL and Neo4j as our representative product for the SQL database and the graph database, because these two products are the most popular and widely used product in the academia and the industry. So the experiment in our case is run on the same hardware machine to make a fair comparisons. So we don't want the difference of the performance is due to the strength of the machine. And to simulate the distributed environment for Spark, we use each CPU core on the experiment machine to simulate a single worker node in the class environment. And for the first task of trace link generations, we will generate the links between the GitHub issues and the commits with the ensemble models. So the commits will contain the source code as change set, which is like what the source code has been modified in this commit. And the ensemble models contain 3 submodels. The first one is a vector space model, and the second one the n-gram vector space model, and the third one is LDA models. These 3 models will create their results individually and then send their results to a voter. The voter will determine the final result based on the majority and agreement of the three models. And the data we used for this experiment is collected from the GitHub. And as you can see, this project are from bigger organizations such as Alibaba, Baidu, and Meituan, and Tencent. So we sorted these projects according to the candidate links we will need to create. And we can see the BKCMDB project has the largest population of the chase links, which can achieve around 3 million candidate links. And the result of the chase link execution is demonstrated as the following. As we can see, the blue line represents the performance of Spark, and the orange line represents the performance of Java, and the time is represented in the seconds. As we can see, as the project size increase, the Spark can maintain a low level of execution time, whereas the Java cannot. So this result shows that the Spark-based implementation can scale with the project size, where the Java-based approach cannot. And in the largest project, we can see the Spark-based method can achieve around 74 speed up than the Java-based method. And for the second task, we're tracing from the bug report to the commit and then the code files. The example queries we used for study is that return a list of source code files which are related to all the open bug reports. So we're actually finding the bug reports for the current code base. And the project we use again is from the GitHub. And this is like multi-hop queries. So we have 2 type of links. The first link is the link between the bug report to the commits, and we represent as link 1. And the second type of link is the link between the commit to the code, we represent as link 2. We also sort this project into according to their total links. We demonstrate the result in the following figures. There is 5 lines of the figures. The blue line indicates the performance, the execution time for the Spark model, the Spark-based implementations. And the red one refers to the Neo4j database execution time with the warmed up cache. And the orange one referred to the Java implementations. And the green one referred to a graph database execution time with a cold start. And finally is the SQL performance. As we can see in these figures, the Spark can achieve an overall best performance, and even the link size increase, the performance can stay very low in 10-second level. And we noticed that the Neo4j performance varies a lot. When start with cold start, the Neo4j performance is not very efficient. But once we apply with a warmed up cache, this core execution engine can achieve a similar performance as our Spark-based approach. So in practice, the performance of Neo4j should be at some point in the middle. But anyway, like the Spark-based approach can outperform the Neo4j performance even with warmed up cache. And in addition to the benchmark evaluation, we also applied our approach to real-world electronic health record systems. In this case, we try to understand, we try to issue several queries and understand the source code of this project. What Vista is a system containing 4 types of artifacts, including the HIPAA and the CCHIT, and most importantly, the requirements and the source code. This project, however, this project do not contain any trace links during the software engineering development. So in this case, we will apply our approach to answer 2 queries. The first is that which requirements are implemented in a cross-cutting way. And the second query is that which codifiers are related to security functionalities, and also which requirements are associated with those source codifiers. As there is no link exists, we will first generate links and then use the generated links to answer these queries. The result of the first query is demonstrated as the following. On the left side, we have a list of the requirements, and on the right side, each column is represented as modulars, and the cell, the blue cell in the tables, indicating that this requirement is strongly associated with specific modulars. And with these figures, we can easily identify which requirement is actually cross-cutting. For example, for the first two rows, we can find that there is a lot of blue cells. So these 2 requirements are actually very cross-cutting, and their implementation are across all over the modulars and not encapsulated in a single modular. And the second query's result is also shared as follows. So we firstly execute the query to retrieve the security-related code from the code base, and this result is shown on the left side. And we highlight the security-related concept in the source code. And then we use the trace links between the source code and requirement to retrieve the related requirement for this code. And after the manual evaluations, we find that the first result recommended by our models is actually related to these code files. So by this way, we answer both the query 1 and the query 2. So to wrap up and summarize, in this work, we propose a Spark-based method to generate trace links and execute the trace queries. Our benchmark results show that the Spark-based method is significantly more efficient than the conventional Java-based implementations. In the aspect of the query executions, Spark-based method also can outperform relational database and the graph database, which is proposed in other studies as the optimal solution for the traceability in the industry scale. And in addition to the benchmark evaluation, we applied our approach to Water Vista project to demonstrate that our tools or our approach can be used for the practical user queries. So thank you for your attention and listening. This work described in this paper is all funded by the NSF grant. So thank you, and see you in the conference.